My name is Gustavo Anjo. I'm a researcher at the Institute of Telecomunicações on the Optical Quantum Communications group. We are in one of our labs at Aveiro. So the KKD platform that runs a continuous variable protocol is implemented in here. So what you are seeing in here are two KKD nodes. So we have one KKD node and a second KKD node. Each KKD node is composed of a transmitter and receiver device. So we can identify in here the transmitter device on this part, and the receiver device of the node of the first node is in here. Starting by analyzing the transmitter device, everything starts on a KRNG, a quantum random generator model that is installed on a PCI Express card of this tower. That quantum random generator module generates a sequence of bits that are processed in a digital domain by a field programmable gate array, which what you are seeing in here. This FPGA, it transforms the sequence of bits on a signal that is then used to modulate a continuous wave generated by a laser. That modulation occurs in this IQ modulator. So the key information, it's on this device that is mapped on the laser on a continuous wave that is posteriorly attenuated to generate the coherent states that are transmitted through the channel. The receiver device. So the receiver device, contrarily to the transmitter one, the transmitter device, the DSP runs on a graphical processing unity, also installed on the tower. In this case, we perform a heterodyne coherent detection, where we receive the signal, the quantum signal carrying the key information, and we mix that quantum signal with a local oscillator that is independent of the transmitter laser. After performing the coherent detection, we scan the signal in a digital domain, and we transfer the signal to a graphical processing unity to run the DSP. In this type of systems, we operate the protocol with a very high quantum bit error rate, around 40%. So when I exchange the quantum information through the channel, the key at the transmitter side does not match the key at the receiver side. So we have a bit error rate around 40%, and to generate a symmetric key, we have to correct the errors, we have to reconciliate the key, and we perform that also on a graphical processing unity. So after implementing the low density parity check codes that we use to reconciliate the key, we get a symmetric key between the transmitter and receiver device. These kind of systems, they are quite heavy in terms of processing load, not just the digital signal processing chains that run at the physical layer, but especially the post-processing algorithms that are responsible for the key reconciliation, the privacy amplification of the protocol, and also responsible for the channel monitoring that we use to search for eavesdropper signatures. So at this side, this KKD node is exactly equal to this one that I just described. In this setup, we have a transmitter device of this node connected to the receiver device of this one. The transmitter device of the first node, this one, is connected to the receiver device of the node that we have installed on IT1 building, not on this building. We'll just see the third node that we use. So this is, we have implemented a mesh topology of 3 nodes. So let's go now see the third node.